Hello, Physics 30s. Here we are today talking about Lesson 4, Unit 5, the Compton effect. This is just a link. I tried to play it for you. It's the NWA straight out of Compton clean version, but it sounded just terrible on this program, so I'm not going to play it for you. This Compton effect has absolutely nothing to do with the city of Compton or NWA. It is a scientist Compton, not the settler Compton, who again had absolutely nothing, but there's a fun connection there. So this is the Compton that we're talking about. Compton was the first person to ever provide conclusive evidence for photon theory. So actual evidence that says, yes, light is acting like little tiny particles called photons that also have wave-like properties. And here is Compton, and here you can see in the background the Compton equation. So here's the idea with this. Here's the Compton experiment and the big ideas. So Compton blasted high frequency, short wavelength, high energy X-rays at a very extremely thin carbon foil. And you might recognize that, if an electron gets kicked out, we've got our photoelectric effect. So that's not really too much of an issue there. But wait, what? What? There's a deflected X-ray with a longer wavelength and a lower frequency. This was a bit of a surprise for Compton and all the other scientists that were working on this in the time. So let's explore this a little bit further. And again, this is the Compton effect, that deflected X-ray with a longer wavelength and a lower frequency. So the Compton effect, what we've got here, actually defies classical theory in two very big ways. Remember, classical theory is treating light as a wave. So the first problem was, well, the X-ray is entering the carbon. What's the angle of incidence here? Angle of incidence, so if I draw a normal line down the middle here, my normal line, angle of incidence, theta I is equal to 0. And you may remember from, well, Unit 4, I suppose, when the incident angle is equal to 0, the refracted angle should also be equal to 0. So it should just pass straight on through, right, with no deflection whatsoever. But clearly it was deflected, right? So that doesn't make any sense when we're talking about waves passing from one medium into another. The second problem, and this is a really big one here, is when we're talking about a true wave, what never ever changes? The frequency doesn't change. So it shouldn't deflect and it shouldn't change frequency, but here we are, we've got EMR that has changed its frequency. Its frequency has decreased and its wavelength has increased. That is not something that happens with waves, not with true waves anyways. So how did Compton explain this behavior? Well, let's jump right into it. Might remind you of something, to be totally honest. So forget about it as a wave. Now think about it more in terms of this EMR. Think about it more as a particle. So a particle smashes into another particle. One deflects this way, the other deflects this way. It loses some momentum and energy. This looks exactly like a collision, a 2D collision from Unit 1. What types of things collide? Well, it's particles are colliding, right? And photons are now behaving like particles, right? As if they have momentum. We talked about before, momentum is the product of mass and speed, but photons don't really have a mass, so there's a bit of an issue there. So what Compton did, and this is pretty smart, is he figured out the equivalent momentum of a photon using the equivalent mass. And here we go back to Einstein. You remember Einstein's most famous formula that we're finally getting an opportunity to use, E is equal to mc squared. So what we're looking at is if a photon had mass, this is how much mass it would have, or this is its equivalent mass. So I'm going to rearrange this. M is equal to the photon's energy divided by the speed of light squared. And we know how to calculate that, right? So my momentum then, P, must be equal to, okay, so the mass, well, that's the photon energy divided by the speed of light squared times the speed, but wait a second, it's the speed of light, so that's actually going to cancel, and we end up with our, and it's rearranged a little tiny bit here, but we end up with our momentum formula for photons. E equals P times C, where E is the energy, and it has to be in joules. C is the speed measured in meters per second, and P is the momentum of the photon in kilograms meters per second. Pretty cool stuff. Pretty cool stuff. So we can expand on this a little bit because we know that the energy of a photon is either Planck's constant times the frequency or Planck's constant times the speed of light divided by the wavelength, which now leads us to a couple extra formulas for the momentum of a photon. So we got P is equal to hf over c, and we got P is equal to h over lambda. And things that you need to note for this, because we're still using kilograms, meters, seconds, stuff like that, the version of Planck's constant that we absolutely 110% have to use is the one with joule seconds rather than electron volts. So we're sticking with joule seconds. So in summary, if we're ever dealing with particles, things that have an actual rest mass, so you can hold them still, they still have a mass, we use momentum, it's mass times velocity. So protons, alpha particles, electrons, trucks, you name it, P is equal to mv. For high energy photons like X-rays and gamma rays, we use E is equal to P times C, and then we just saw how we could expand on that by a little bit. So check out a quick example here. How fast would an alpha particle have to move to have the same momentum as a 7.3 mega electron volt photon? So first and foremost, we just spent so much time talking about how it needs to be in joules. Energy needs to be measured in joules. So let's go ahead and change that to joules. 7.3 times 10 to the, so mega electron volts, that's 10 to the power of positive 6 electron volts. Let's see, I want to cancel electron volts. Let's put those on the bottom, end up with joules. It's 1.6 times 10 to the negative 19 joules for every 1 electron volt. Nice. Go ahead and plug that into your calculator. Good, good, good. And hopefully we all agree that we are getting 1.168 times 10 to the negative, better double check, 10 to the negative 12 joules. That's a very high energy photon, actually. Yeah, very high energy. Cool. So now that we've got that, now we can go through, and there's a couple different ways that we could solve for this. We could go through and we could say, let's solve for the momentum of that photon. Then separately, let's say, okay, now that we have the momentum of the photon, let's use that momentum to figure out the speed. Or alternatively, we could say, and this is a bit of a shorter way, we could say the momentum of the alpha particle is equal to the momentum of the, I'm going to put pH for photon. So those two things have to be the same. So let's see. This one is going to be m times v, and again, we're talking exclusively about the alpha particle here. And on the other side, well, the momentum, the formula that we've got is E is equal to P times C, so P must be equal to E over C, absolutely, so E over C measured in joules. Okay, so then I'm looking for the speed. Let's see, so I'm multiplying by mass, I just need to divide both sides by the mass. Now I'm going to be very clear here, this is the alpha particle that we're talking about over here, and everything on the other side we're talking about the photons. So, cool. So the speed of the alpha particle is going to be equal to the energy. So that's 1.168 times 10 to the negative 12 joules divided by c, 3 times 10 to the power of 8 meters per second. And also divided by the mass. Now the mass of an alpha particle, you might not have that one memorized. Any ideas where you could find it? If you're thinking your data sheet, you are absolutely correct. 6.65 times 10 to the power of negative 27 kilograms. Maybe just have a quick look if you didn't to see where that's coming from. And take a second to plug that in. And again, hopefully we get to the same spot. So the velocity of the alpha particle should be equal to 5.85 times 10 to the power of 5 meters per second. Cool. So our first question ever dealing with momentum of a photon. Very, very, very cool. So yeah, we're familiar with the idea. Still doesn't really explain much of the Compton effect, but we're getting there, right? Because now if we're treating this as if it should be 2D momentum, well, now we know how to figure out the momentum of a photon. Very, very cool. Okay, so what Compton did with this to fully explain this and come up with his momentum formula is he actually combined the law of conservation of energy and the conservation of momentum. So applied both of them to come up with this. So first and foremost, let's talk about the conservation of energy. So conservation of energy is ETI is equal to ETF. So before anything happens, we've got the energy of the X-ray. After, we've got some kinetic energy for the electron, and we've got the photon energy of the X-ray after. One important thing to note with this is a scalar equation. So directions, you do not need to use directions whatsoever in this. You can't use directions anywhere in this. So scalar only, no directions. The second piece that he looked at was our conservation of momentum. This is a 2D conservation of momentum, so it will require a little bit of vector analysis. And because momentum is indeed a vector, we have to include directions. We have to include the angles of both the electron and the deflected X-ray, and, well, realistically, the incident X-ray as well. So if we look at our conservation momentum, our total before is our total after. All we've got before is the momentum of the X-ray, and if I want that, I have to add up the electron after plus the momentum of the X-ray after. But keep in mind, again, it is 2D. I can't just say 6 plus 4 is equal to 10. We have to add it in 2 dimensions, which in its easiest form is tip to tail, and its a little bit trickier form is dealing with components. All stuff that we've done before, all stuff that we can do. So again, he combined those two ideas, and you do need to be able to deal with each of those independently, and we'll look at an example soon enough. But he combined them to come up with his equation. Here is his equation. To determine the change in the X-ray's wavelength, so here we have change in the X-ray's wavelength, it is h over mc times 1 minus the cosine of theta, where m is typically the mass of the electron. Now you might see the odd question in your workbook where it's using a proton. It's the only thing with mass in it. So if you're using an electron, use the mass of an electron. If you're using a proton, use the mass of a proton. 99% of the time you'll be using an electron. And h is Planck's constant. It has to be the one with joules, needs to be with the one with joules. C is obviously the speed of light, and we'll jump into those other pieces a little bit more. So first and foremost, the change in wavelength, well, if we're ever dealing with change in anything, it's final minus initial. So sometimes questions might give you the initial wavelength and ask you for the final wavelength. So if we can solve for the change in, we can solve for the final wavelength. Cool, so that's one quick note, is change in anything, final minus initial. That didn't go anywhere. The second note, theta is very, very, very specific. Theta is the angle of the X-ray deflection with respect to its original direction. So where it would have gone with no deflection. So where it would have gone with no deflection, straight along this dotted line, where it's actually going down here. So that is theta, right? And it could be more than 90 degrees in this case, realistically, right? So even before we jump into this example, let's figure out first off what theta is. So I've got my incident X-ray coming in. Let's go back to that nice purple felt pen that I had there. Is that it? Yep, there we go. So the incident X-ray coming in, smashes into an electron. The electron moves off at 21 degrees. The deflected X-ray looks like it's going up at 17 degrees compared to the vertical there. What is my actual theta that I want to use in the formula? So compared to its original path, the original path with no deflection for that photon is going to be right there. So theta that we use in our equation is right here. So it's 90 plus 17. It's actually 107 degrees. So always compared. Cool. So I know that there are actually 3 parts to this, A, B, and C. For now, we'll focus on A and B. So part A, the wavelength of deflected X-ray given this information. Cool. So let's think about some ideas here. Some big ideas. We could use physics principle 5, physics principle 4, or our Compton equation. Those are our options for this because those are all things that work for this situation. So if I were using physics principle 5, that's ETI is equal to ETF. Let's think about that. We don't use any directions, but I need the energy of the X-ray before, which I could get because I have the wavelength. I would need the kinetic energy of the electron, which I have nothing for. I don't have the speed, so I can't find it. And also, I have nothing for this. So there's too many unknowns for conservation of energy. Conservation of energy is not going to work for me, or for any of us, realistically. Okay, so physics principle 5 is out of the question. Physics principle 4, conservation of momentum. I could figure out the momentum of my initial X-ray. Don't have the speed, so I can't figure out the momentum of the electron, and again, too many unknowns. So we have to use then our Compton equation. Now, did I give myself space for this? I kind of did, sort of. Sort of. I should have planned that out a little bit better, but that's okay. We can always work on this. Okay, so for part A, we're using the Compton equation. I've got it written out down here. You might want to write it out again in your notes. So first thing that I would do, if we're looking for our final wavelength, an easy thing to do would be to solve for my change in wavelength. So change in wavelength is h over mc times 1 minus the cosine of theta, and we just said before, theta is actually equal to 107 degrees. Cool, so h, we make sure that we use the one with joules, 6.63 times 10 to the negative 34 joule seconds. We're going to divide that by the mass. In this case, we're using an electron, 9.11 times 10 to the negative 31 kilograms. And then c is the speed of light, 3 times 10 to the power of 8 meters per second. And then we're going to multiply this whole entire thing by 1 minus the cosine of theta, so that's 1 minus the cosine of 107 degrees. So go ahead, I want every single person to try to plug this into their calculator because this can be a little bit trickier. Honestly, what I would do 1 minus cos 107, get my answer, and then I do that times 6.63, 10 to the negative 34 divided by 9.11 divided by 3 times 10 to the power of 8. But just make sure, take a moment, plug it in, make sure you get to the right place. So if you're getting 3.135 times 10 to the negative 12 meters. That is perfect. That should be good to go. I'm going to take this one step further, and I'm going to actually put it into picometers because my other one's in picometers as well. So we'll need to do some sort of conversion somewhere. And let's see, so that's 3.135 picometers, which by the way are my favorite units in physics. They're just so dang cute, picometers. Cool, so this is my change in the wavelength. If I wanted to figure out my final wavelength, well, it's easy. I just say change in wavelength is equal to my final wavelength minus my initial wavelength. So let's see, final wavelength must be equal to my change in minus my initial. Nice. So my change in, 3.135 picometers. My initial, I better double check, I think it was 2.8. Yep, there it is right there. 2.8 picometers. And when we plug that in, it works out to be 5.94 picometers. So my final wavelength, or my wavelength after the collision happened, 5.94 picometers. Cool, so not so bad. The Compton equation, not so bad. Let's go back. Let's check out now what the other parts of the question were asking us for. So I'm going to rewrite this because these are still in my top left corner here. These are still the three big ideas. So Compton equation, I'd say we could probably cross that off because we used that for part A, right? Definitely use that for part A, and I think we've exhausted options with that one. So for part B, if I'm looking for the kinetic energy, I think it should be pretty obvious. Kinetic energy, that sounds like physics principle 5. That sounds like conservation of energy. So let's check this out. Okay, good. Should have erased all that stuff, but that's okay. Here's my conservation of energy, and here's the information that we've got. Now remember, this theta was 107 degrees, and we also figured out the wavelength of the deflected X-ray. Cool, so my conservation of energy, I really should have cleaned this up. I apologize, folks. That's okay, we can start with this. ETI is equal to ETF. You'll have to write that out. I'm kind of lazy and didn't erase it, so it's already there for me. When I expand on that, though, my initial energy is just the X-ray before the collision. Then where all that energy goes is it goes to kinetic energy of the electron plus the photon energy of the X-ray after. So let's just, once you've got that written out, let's just start to expand on that a little bit. Now, notice with the diagram up here, we've got wavelengths. So wavelength after, wavelength before. So I think for my photon energy, I'm going to use hc over lambda. And kinetic energy, I think the question is just asking for kinetic energy. We could find the speed, but I don't think we have to. Plus hc over lambda after, and remember after and final will be essentially the same thing. So my kinetic energy is going to be equal to hc over the wavelength before minus hc over the wavelength after, and we got to plug some numbers in. Please make sure that you are using the correct value for Planck's constant, 10 to the negative 34 joule seconds times 3 times 10 to the power of 8 meters per second, all divided by the wavelength before. So what was that, 2.8? We want to have this in regular meters now, so times 10 to the negative 12 meters, and then subtract from this. This is going to get a little redundant soon, but don't be lazy. We can write it out. 6.63 10 to the negative 34 joule seconds times 3 times 10 to the power of 8 meters per second, and then divide that whole thing by, what was it, 5.935 or something? Let me go back up there. Yeah, 935 times 10 to the negative 12 meters. Cool. So plug that one into your calculator. Give you a second to have a look at that there. Plug it into the old calculator, and we should end up with 3.75, sorry, times 10 to the negative 14 joules. Cool. Very good. That's the final answer for this part B. That being said, excuse me, could you take this one step further? Could you figure out the speed of that electron? Absolutely. I'll just do this off in the corner over here. EK equals 0.5 mv squared. You could take that one step further. You could figure out the speed. That's not an issue for you. You've got this. Cool. The last one actually doesn't have too much math involved, if I'm being totally honest here. The next, not the last one though. I may have said the last one. The last one's a little bit more mathy, but definitely doable for this. Okay, that's just the answer there. Part C is sketch the vector sum diagram, in other words, the tip-to-tail diagram that illustrates the conservation of momentum. That being said, as I go through and as I look at this one, it's just the diagram, right? So there's not a ton of math involved. Cool. So I want to go through and very clearly, we're using physics principle 4 for this. Physics principle 4, conservation of momentum. And my conservation of momentum says, let's put that right there, I suppose. My total momentum before is equal to my total momentum after. So before, I've got the momentum of the X-ray. After, I've got the momentum of the electron plus the momentum of the X-ray after. Right? And remember, way back when in the original question, it says that the electron is originally at rest. So that means the only thing that's got any momentum is the X-ray before. Cool. So I know that I need to add these two things together, and they should make this, right? So these two things that I've got underlined in blue, those we add tip to tail. And then the thing that I've got underlined in black, that is my resultant, or my overall. Cool, I think we can do this. Absolutely, I think we can do this. Let me get that nice purple felt pen back. So let's see. The momentum of the electron is coming down at an angle like this. Nice. I need to add to that, and I could add to this in one of two places, the momentum of the X-ray. So it has to be tip to tail. So I could put the tip of the X-ray after, I should say, there. The momentum of the X-ray after is coming up at an angle kind of like this. So there is my momentum of the electron. There is my momentum of the X-ray, and these are both after. They're being added together, and I know that because it is tip to tail. And then my resultant, I'm going to make it a dotted line. That's my momentum of my X-ray before. We could even, like if we really wanted to, we could put a couple angles in here, right? We could definitely put in a couple angles. So the X-ray after compared to the horizontal was 107 degrees. So we could put 107 degrees there. And then my momentum of the electron, I could put, so compared to the, let's see, actually start off over here. Momentum of the electron was 21.6 degrees compared to the horizontal. And then that's actually going to form a like angle right here, 21.6 degrees. So we could add a couple angles. The question didn't really ask us to, but we definitely could have. So again, comes back to adding things in 2 dimensions. Awesome. Okay, I have left myself tons of space to work here. The next example that we want to look at is a bit of a big one. It's a bit of a doozy. If you remember back to Unit 1, it is conservation of momentum in 2 dimensions where we have to add things tip to tail. So just as a bit of review, there's really only 3 steps to this. 3 steps. Step 1 is break everything into components. Every single vector that you've got, break it into your x and y components. Step 2 is deal with x's and y's separately. So add up all your x's, do the math in the x, add up all the y's, do the math in the y, do what you got to do in each of those. And then step 3 is solve new 90-degree triangle. Right? I should have made that a 90-degree triangle. It looks more equilateral. Cool. So it's just those 3 steps. We've been dealing with those a ton in Unit 1. It's, you know, we can deal with them now. So, excuse me. Let's go through and let's start to break things up. What did I leave myself for space here? Oi, I did not do myself any favors today. So I'm going to start with, what is this? This is the X-ray before. So the momentum of the X-ray before in the X component is going to be equal to, well, that's just 50 atto-Newton seconds. That's easy. What about in the Y component? In the Y component, well, all of it's horizontal, so none of it's in the Y component. I love these ones when you're breaking them apart like that. So that's our X-ray before. Let me just, this might go in a bit of a wonky order here. Let's look at my momentum of the X-ray after. Cool, and maybe I'll even do this in a different color just to make it stand out a little bit more. Momentum, X-ray, after. Yeah, that looks neat. Okay, so let's see, my Y component is going to be here. Momentum after in the Y, momentum after in the X. Nice. So my Y component, it looks like if my angle is right here, it looks like that's the adjacent side. I should be using cosine. So momentum in the Y component after is going to be equal to the cosine of 30 degrees, or the cosine of theta, times 40 atto-Newton seconds. Go ahead and plug that one in. I think that's going to work out to be negative 34.64. And of course, atto-Newton seconds. Atto is just tiny. I believe it's 10 to the negative 15, by the way. Okay, so then let's see. My momentum in the X after for this one. Let's go through, and so I already used up cosine. The chances are this is going to be sine. Let's just double check. That is indeed the opposite side. So good. So sine theta. You know what? We're taking a few little shortcuts here. Let's do sine of 30 degrees. It'll be a little tiny bit easier. Times our 40 atto-Newton seconds. Good, good, good. So let's see, that's going to work out to be, plug it in. We got negative 20 atto-Newton seconds. Now, I didn't mention this, but the negative, right, when we're dealing with explicitly X and explicitly Y, well, the Y component's going downwards and the X component's going towards the left. So when we're dealing with them individually, we can go through and we can call them positives or negative. Down, typically negative, up, positive, left, negative, right, positive. Cool. So now what we want to do is we want to deal with our conservation momentum in the X and our conservation of momentum in the Y, and we want to treat those separately to figure out the missing components for the electron's momentum. So let's go ahead and do that. I really like working in green, so I might go back to my purple here. So I've got total momentum in the X before is equal to total momentum in the X after. So let's just go through. So total momentum in the X before is, let's see, X before, that's just 50 atto-Newton seconds that's coming from up here. Then after, I've got, okay, so after, and we're dealing with the X, I've got this over here. That's negative 20 atto-Newton seconds plus the momentum of the electron after. So the momentum of the electron after must be equal to 50 minus negative 20, or in other words, plus 20 atto-Newton seconds. So that should be 70 atto-Newton seconds. Cool. So I am kind of skipping a few steps here. I hope you're following along all right. But we're just looking at the X. So X before just comes from the X-ray up here. X after comes from both the X-ray after as well as the electron, and it's the electron that we're actually trying to solve for. So we figured out the momentum of the electron after in the X component. I should be very, very specific that this is just the X component. Cool. So if I add that to my diagram up here, I just figured out this. 70 atto-Newton seconds. Cool. If I want to figure out that angle beta, all I need to do is figure out that. So let's go ahead and let's solve for that. So I'm going to be looking at my conservation of momentum in the Y component now. So PTY before is equal to PTY after. Beforehand, I have nothing in the Y component because look at what I got up here. Where is it? I'll highlight it in blue. Before, the only thing I got is the X-ray from before, and I've got nothing in my Y component. So that's cool. That's fairly easy. Let's, is this going to take me back? Yeah, that's going to take me back. And then after, I've got, let's see, my y component of the X-ray. So that's going to be negative 34.64 plus the momentum of the electron in the y component after. So the momentum of the electron in the y component after, well, this is really easy math, must just be 34.64 atto-Newton seconds, but it's got to be upwards, and that actually matches our diagram up here. So 34, I'm going to erase that question mark and say 34.64 atto-Newton seconds. Cool. I got a bit of a mess on my hands here. So I might just make a new diagram rather than using the one that's up there. So for my electron, here's the momentum of the electron after. I've got the x component, we said was 70 atto-Newton seconds, and the y component, we said was 34.64 atto-Newton seconds. And the question isn't asking us for the overall momentum, it's actually just asking us for the angle. We totally could solve for that overall momentum, but we just need the angle. So the angle, let's see, theta is going to be equal to inverse tangent of the opposite over adjacent. So the way that I've got it drawn here, the opposite is 34.64 divided by the adjacent, which is 70. And go ahead and plug that in. We should be getting 26 degrees, and I realize I made a bit of a screw up right here. We're not looking for theta, we're looking for beta. There we go. Beta is 26 degrees. Cool, so that question really wasn't new at all, other than that we're using very, very, very small momentums. It's exactly what we did in Unit 1, and like I say, it comes down to conservation of momentum in 2 dimensions, which is break everything apart into components, solve for what you're looking for in the x, solve for what you're looking for in the y, solve a new right angle triangle to solve, well, the entire problem. In this case, looking for the angle. Cool, very, very cool. So I'm pretty sure I would have left myself a bunch of space knowing how this one kind of went. Some cool applications of this, solar wind sails. You read about these in sci-fi novels and every once in a while in the news too. Is it better to use a highly reflective or absorbent material, do you think? Probably say reflective so that the x-rays bounce off and they can actually push those solar sails. Another place where we see this is cosmic lenses. Right? So this is one piece of evidence for dark matter and for black holes. So if light has momentum, it should be affected by gravity. So it bends as it passes around large masses like large stars or large chunks of dark matter or even black holes, which is pretty cool. This is explained by Einstein's theory of relativity, showing that light has mass, right? Or at least equivalent mass, which is pretty cool. So that's our lesson. I know it's a bit of a long one, but this week you've got a couple short ones and a couple that are a bit more reviewy, so not too bad. Anyways, do some practice. Please let me know how things are going, and we'll talk to you again soon, Physics 30s. Bye for now.